Good afternoon. I believe it's afternoon in Sofia, although some of us might be in different time zones. My name is Michał Antkiewicz. I am a doctoral school student at the Wrocław University of Science and Technology. And today I would like to present you our work on improved gap memetic-based differential evolution, which is applied to multimodal optimization. So I will start with explaining our optimization space. Then I will introduce the base Gamidi algorithm, which was the starting point for our experiments. Then I will explain the improvements we decided to apply to this algorithm. And in the end, I will present the results of the experiments we conducted on 3 benchmark sets and compared to 3 reference methods. So we work in continuous space, which means we work on floating point numbers and we have bounded space. So in our multidimensional space, which is in our data set from 1 up to 20 dimensions, our functions are strictly bounded. So every point, every point in all those dimensions inside those boundaries is a valid point. And as you can see on this example here, if I can draw over this, the x and y axis, they are bounded from values -5 to 5, and the value of point in each of those areas is marked on the axis z. So as you can see in this instance, we have 6 different global optima in this space. This space is approximation of the landscape of this function we achieved by sampling the space. So of course, we also have multiple local optima. A lot of those peaks are local optima, but we seek only for the global optima in this case. And we use peak ratio metrics, to define the effectiveness of our algorithm. So it is simply number of optima we found during the whole run divided by the number of optima that are present in this instance. So if we find 3 out of 6, we have 0.5 peak ratio. And there's also success rate, which defines if we found all optima or not. So 1 means we found all of them, and 0 means we did not found all of them. So if we just missed 1, it's still 0. And of course, we have accuracy. This is the accuracy we used in all the experiments. It's 10 to -5. Because as I stated before, we use floating point numbers, so there's a chance we don't hit the exact number, but if we are close enough according to this accuracy, we consider it to find the optima. So for our benchmark sets, we started with the most commonly known sets 2013. It's used in many competitions, and it was actually used in the competition where Gamidi algorithm was originally developed for. It contains 20 different instances, where 10 of them, those marked with CF prefix, are compound functions, which means they are composition of simpler functions, but they are sometimes translated, rotated, they are inversed. So different operators were applied to create those composite functions. But as I said, it was used for development of this algorithm, and it was the competition. So as we might predict, algorithms tend to overtune, to overfit to those benchmarks used, and it's hard to apply those overfitted algorithms in general in the real world applications. So we wanted to check how good this algorithm generalizes for other functions. So we found the alternative benchmark set, which we called classical functions because it contains many of functions that are commonly used in the literature. So it has a bigger variety of functions. It introduces 5 new functions that were not present in the former set. And for those that were, it significantly restricts the budget. It very often, in many cases, it reduces it 5 times. So we have much less evaluation functions to sample the space. So it's a bigger challenge for those that were present in the former set. But there are also three trap functions, which are also called deceptive functions. And deceptive functions, they tend to have easy to find local optima, which are not global optima, so they mislead algorithms to fall into those local areas. While the actual global optima is hard to find, it's far in the corner of the landscape, or it's very, very narrow. But unfortunately, there are only one-dimensional deceptive trap functions, and we thought we would like to test our algorithm on multi-dimensional trap functions. So we proposed a simple formula just to average those functions across multiple dimensions. So we expanded those three instances up to 2 and 3 dimensions. As you can see on this image below, we have two-dimensional variants presented here. So we have just one global optima here in the corners, and for the D6 instance, we have 4 optima in the corners and many local optima in the middle. We also have three-dimensional variants of those functions, but obviously it's not easy to present them here. Here's the alternative visualization of them. Maybe I can just move it somewhere here. And yeah, so here's the other view. And now we conducted some preliminary experiments using our GAMIDI, the basic GAMIDI method, which was developed for the competition on niching methods for multimodal optimization in 2020. It took second place, so it was a very good algorithm. But as I said, it was just a benchmark set. And the one that was very well known. It used a backbone of this algorithm was differential evolution, so the standard method of creating new population in continuous space optimization, but it also used the hill valley clustering, which is getting more attention in the last few years. So hill valley clustering is a very simple idea, yet efficient. It uses hill valley test. So if you are not familiar with this, if we have 2 points, let's say A and B, and we consider it as the maximization problem, so we want to have the highest value, we can perform hill valley test between those two tests. In the most simple way, we use 1 point for the hill valley test. Now, if this point is below those two, so it's worse, we can assume that those 2 points are in 2 different hills, as it is in this case. So we have 2 different possible directions to research. So we leave all those 2 points. But if we had B and C and we compare when we perform a hill valley test between them, so we have this point, it means that probably they are on the same slope of the hill, they are on the same hill, so we don't need all 3 of them. So we can remove B and Y and we just leave the best one because they are on the same hill and we don't need this redundant information. And then it uses amalgam, which is the estimation of distribution algorithm for the local search around the hill. So if we have some points on the hill, we can perform the local optimization for this place. But it were standard, maybe not standard, but it were already known solutions. But the most important novelty in the original GAMIDI algorithm was the gap selection operator, which is very similar to standard tournament selection operator. While tournament selection operator it prioritizes individuals with the highest fitness, so those with higher fitness have higher chance of being selected. In our case, in gap selection operator, it prioritizes those points with higher gap value, where gap value is the distance to the nearest point in the R-hive. So we simply prioritize points which are further away from those we already found in the R-hive. And it appeared to be working very good in the original algorithm. So I will not go into the detail because we don't have time for this, but very quickly, general scheme. We start with random initialization, and this basic algorithm, it has 2 phases. It has white and focus phase. It starts with the white, and for the first run, it just goes straight to the random selection. So after random initialization, it uses random selection out of this population. It creates another population using differential evolution, it goes to the archive. So it stores the promising values, promising solutions in the archive, and it decides to switch phase. It is based on, there's a parameter, I think it was hard-coded in the original algorithm, like to 3. If it found 3 new optima, not global optima, but some optima, it starts hill climbing just to tune those promising optima. Then it returns to the new population, and if it was white, it again uses random selection. If it's focused, it uses one of those two selections because there is another hidden parameter, that's a hidden switch. It uses either tournament, standard tournament, or a gap selection based on, I think there was just a switch every 5 iterations it was switching. So again, hidden parameter here. So we decided to simplify it a little bit, get rid of some hidden parameters, those switches if they are not needed. We conducted a preliminary experiments on this new data set we called the classical functions. We compared it with 2 different algorithms that are present in the literature. We have hill-vary clustering. It was, I think it was last year algorithm, and double layer clustering algorithm. I think it's probably 1.5 years old, and unfortunately we didn't receive codes of this double layer clustering algorithm code, so we just used those published in the article. They use the same budget and the same instances as we. And for the hill-vary clustering multi-objective, we just rerun all the algorithm. And basic Gamidi algorithm, we noticed that it underperformed significantly on those 3, but mostly those 4 instances, B8, B9, and B10. So we wanted to verify why that happens. But also we noticed that it maintains better results on this B14, which has plenty global optima. So we see value in our algorithm comparison to other algorithms in the literature. So here are 3 different instances that we found problematic. This first one, Himmelblau, it has 4 optima. This Camelback, it has 2 optima, and this Seckles Foxholes, it has just 1 optima, which might be surprising because it looks like it has 25 optima, but it has just 1. I think it's this one, while all the others are just far enough from this optima to not be considered as the global optima. Yes, we propose 4 different modifications. The first one, to save some budget, to skip first selection. I will explain this in a moment on the scheme. We also removed some phase switching just to simplify the algorithm because it appeared it's not necessary. And also we introduced double initial clustering because at the first run, our hill-valley clustering uses archive. So the archive after the random initialization is not fully saturated. It has random points in the archive. So using hill-valley clustering based on this random initialization, it doesn't give good results. It's sometimes misleading. And we make it double times just to filter out all the noise. So the first modifications, we skip first selection. We notice that our initialization, creating new population out of random initialization using random selection, it just wastes 80% of the whole budget, and we are just left with 20%. So it's not enough for our amalgam local optimization algorithm to find all the optima. As you can see, we find first optima here and the second optima using second clustering. So we don't have chance to go further because we are out of budget. We decided to completely skip this first selection and go straight for the clusterization. And we found all 4 optima, and for the B9 and B10, it appeared to improve results significantly. Also, I'll go to the modification 2 in the moment, but I'll just jump to the third double initial clustering. So as I said, our archive at the start is not fully saturated. So for the first initialization, for the first iteration, we do it double times, but with just a single point test, like I presented before. So in the original method, we had some noises here. There were some points, one here and the other here. The blue points that were misleading, they were not, they were just leftovers after the not exact, not fully valuable hill valley test in the random noise. So we make it double times, we filter out those points, and we just left with those valuables. So our clustering can use points around this this valuable solution of the archive, so it can then cluster and find the optimum. And the same for the compound function 12. There were some noises, but we want to just leave this point here because it's the valuable point in the archive. So after modification, we just left this one, and all the points around that were used to by the amalgam, it helped to find this global optima over here. So it helped even more for those instances. And the last modifications, we wanted to remove those phase switching because it added some parameters and some operators we didn't want to use. So unfortunately, after removing this, our average effectiveness dropped because it appeared to be necessary. It was pretty much overfitted to the benchmark set. But if we combine it with all the modifications we had previously, it appeared to improve, but not very much. But it still simplifies the algorithm, so it's some benefit. Unfortunately, we noticed some drop in the effectiveness on our deceptive function, which was tested after all the modifications were presented, and I will go to this in the end, what happened here. But for the selection, we also removed our tournament archive selection. It's not needed anymore. We are just left with random selection and the gap selection. As you can see, the gap selection works pretty nice because it distributes the population around optima very in uniform manner. While tournament selection, we can see big population around big optima and very small population around narrow optima. And here we can see this distributed very evenly. And yes, for the changes, we remove this first selection. We go straight to the archive because we don't need to create random selection based on random initialization. It doesn't benefit us all. We remove this phase switching. We maintained hill climbing because it's still valuable, but there is no phase switching. We increase the importance of clustering in the first iteration only. And as I said, we remove phase switching, so we don't use it anymore. We also don't use tournament. We just go straight for the gap selection because it was maintaining all the good results, but with less parameters. Here's the new scheme. So as I said, it just simply marks that we just start with complete clustering in the first iteration, and we don't use any phase switching. We just use random selection and gap selection interchangeably. We were trying to use them 50-50 each iteration, but it didn't work out, so we just use it one time, random selection, and another iteration gap selection without any phase switching, any conditions. We just try two different directions, and it turned out to provide the best result for us. So to sum up experiments on these sets 2013, there were no significant changes. We did not expect any because it was the original data set used for development of the algorithm. And for the new classical functions, we achieved much better results. For those 4 problematic functions, we achieved much better results. It's not 1.0, but comparing to double layer clustering, we used the higher accuracy. They used accuracy for this instance is much lower. So if we rerun all the experiments with their accuracy, we achieve higher results. But for the sake of completeness, we just left this result here. And also what is worth mentioning, we achieved better results for this B14 instance, which you might have seen on the image previously, this selection comparison, but there was this, yeah, this one. It was a lower dimensional instance. There were 2 dimensions, and this is 3-dimensional. And none of other algorithms managed to find all the optima even once. So our algorithm found every time all the optima. So it's the bigger benefit. For the deceptive functions, we performed those experiments after we completed all the modifications. It was just to verify how its algorithm generalizes. And we noticed that on this very strict budget, it was very, very strict budget, just to test it. We achieved better results than the basic GAMIDI, but Hill Valley clustering based method achieved better results. And the with higher budget, so if we give algorithms chance to fully run and use all the mechanisms, it maintained the best results. So here's this comparison of the average of all those runs. And one thing to note, our algorithm uses one single configuration for all the instances. We don't need to fine-tune it per instance, what we might see in the literature, but we just use one configuration and run on all of them. And we maintained higher accuracy on all those instances, all those benchmark sets. So to conclude the presentation, we introduced a set of modifications to improve GAMIDI, mostly to improve its use of budget, but also simplify the whole algorithm to reduce number of parameters and operators. And we also proposed a multidimensional deceptive dataset, which we couldn't find in the literature. For the future works, we would like to focus on a more irregular high-dimensional composition of different trap functions, because for now, as you might have seen, they are very regular, just the average across multidimensional functions. And adaptive parameter steering for hill climbing conditions, because we were just using those parameters when to start hill climbing. It was based on the number of optima we found so far. It was a constant value. It works well for all the instances, but we think it should be more adaptive to turn on this hill valley climbing and not just using a plain number. And also, you'd like to balance and prioritize the clusters to explore, because if we have many clusters, we often cannot afford to optimize all of those clusters. Sometimes we need to drop some of them or just to start with those most promising. So there's a still area to improve. And that's all. And thank you for your attention.